Okay, Paulo, please.
So in English, good afternoon. I'm Paulo Nussensweig, Provost for Research at the University of São Paulo, and I'm very pleased and honored to begin our USP Nobel Lecture Series this year. This series is an initiative of the Office for Research that was started back when Professor Krieger was the provost, and then it was kept going with Professor Silvio Canuto as provost. And now we want to make it very active again, both online, but also with in-person events, since we are finally overcoming the pandemic. It is an enormous pleasure to introduce Professor Hoffmann. Professor Borim will give his credentials. I just wanted to say that I'm especially pleased to introduce somebody from Cornell University, where I was fortunate to spend a year as visiting professor. And I tried to reflect that with my background picture, which is a picture I shot myself. So please be very welcome, and we are happy to have you.
Thank you. Let me just share my screen. Can you see it?
Yes.
Okay. So I just have a few words to introduce Professor Hoffmann, because he's a very, very well-known scientist. But I just want to say a few things about him. Professor Hoffmann was born in I don't know how to pronounce his name, but it was Poland in that time, and now it is in Ukraine. And then he moved to Columbia College, where he got his major in chemistry with summa cum laude. Afterwards, he went to Harvard University, where he got a master in physics and PhD in chemical physics. And from 1962 to 1965, he was a junior fellow in Society of Fellows of Harvard University, where he developed his thesis under the supervision of Professor Lipscomb, who was also a Nobel Prize in Chemistry in 1976. In Harvard, he also became interested in structural and mechanistic problems in organic molecules. In that time, he also began his collaboration with Professor Woodward, working on his theory of chemical reactions. In 1965, he was also in the Cornell University as associate professor, and then professor of chemistry, and in 1974, John Newman Professor of Physical Science, and since 1996, he is Frank Rhodes Professor, still in chemistry at Cornell University. I think he has received all the prizes someone in science can receive. I just put a very brief list here, as for instance, American Chemical Society Award in Pure Chemistry, award from the International Academy of Quantum Molecular Science, National Medal of Science. I mean, it's too many prizes to tell all of them here. And in 1981, he was awarded with the Nobel Prize of Chemistry. Can you see my slides or not?
Yes.
Yes? Okay. So in 1981, he received the Nobel Prize, and for the motivation was for their theories developed independently concerning the course of chemical reactions. The prize was shared with Professor Fukui. And I found this very interesting when someone asked him how he knew about the prize. And Professor Rhodes said, how did I find out? I was at home fixing my bicycle, listening to the morning news while I was doing it. Then I heard it on the radio. I immediately ran ran from the garage and called my mother before our phone would start ringing. It's very interesting because I think nowadays nobody listens to the radios anymore. Well, I do. I like radios. And some of his scientific interests is a lot, but I would summarize in this way. I read that he likes to summarize his activity as applied theoretical chemistry, the blend of computations stimulated by experiments and construction of generalized models. Oi? Não. Well, e agora? Well, so I'm sorry. I'm going to start again, okay? This way.
No, don't start again.
No.
Please.
Okay.
You are using the lecture time. Do you want the lecture?
Yes.
Do you want?
Yes. Okay. So this is just to finish. This is what Professor Hoffmann was telling us in 2004. He was here for help people to understand how science is important in the Samba School of Rio de Janeiro, the Unidos da Tijuca. So, Professor Hoffmann, we are very grateful to you for working so hard to make the world a better place for all of us. Thank you, Professor Hoffmann. Thank you very much for accepting this invitation. And during the seminar, I asked the people, please keep your microphone mute. The people in Zoom can ask raising your hand, and the others in YouTube chat just write on the chat, okay? Thank you very much, and sorry for the problem with my slides. Okay, Professor, thank you very much.
Let me
now
share.
You can share your screen with us.
Okay, do you see a red and black slide?
Yes.
Very good. So if you do not see the slides, please interrupt me.
Okay.
Okay, so thank you both for the introduction, for Paulo for showing that picture of Taganrog Falls in back of you, a good memory of Cornell, and Antonio for inviting me. I did not mean to interrupt your presentation, but I need all the time in the world for my lecture.
Yes.
And just to look ahead, this lecture will last 2 hours, and then there will be a break after about 1 hour of about 5 to 10 minutes, which I will announce for everyone to have a coffee. Now, I want to talk to you about chemical bonding. And I can best begin by starting with two quotations. One was of Charles Coulson, who was a very insightful theoretician. And this is caught from an after-dinner talk, not from a written lecture. But he says, will you reflect for a moment on some things that I've been saying? And I'm not going to read it. You can read it as well as I can. It seems to me that a bond between the two atoms is so real, so tangible, that I can almost see it. And then I wake with a little shock. For a chemical bond is not a real thing. It is not an observable. And that is behind some of the difficulties in defining it. And then there is Robert Mulliken, who in his own way, quite consistent with his philosophy, said, I believe the chemical bond is not so simple as some people seem to think. It's been there from the beginning. So a little bit of history. It goes back to the idea of an element. It bypasses one of our founding scientists, Antoine Laurent Lavoisier, because in fact, Lavoisier was not concerned with the idea of a bond or what held things together, but he introduced so much more into chemistry. There comes the idea of valence as chemistry progressed, and then a real explosion in the middle of the 19th century, which is represented by the work of Cowper, Crum-Brown, Butlerov, and Kekulé, where people began to draw chemical structures and graphical formulae for compounds, especially organic compounds. Then there was a period in 1874 where Van Hoff and Lebel introduced the idea of three-dimensionality, the tetrahedrocarbon atom. In the time of the First World War, Lewis and Kossel independently began to view the bond as a shared electron pair. Meanwhile, quite separately, we got the first metrics of chemical bonds, how long they were. I'll say much more about that. And that was the beginning of crystallography and chemical crystallography with the work of many. And then came the old quantum mechanics, the new quantum mechanics in 1926, and pretty quickly the first calculations on the H2 molecule by Heitler and London. And then the development by Pauling, by Mulliken, by Hund of valence bond and molecular orbital theories. You can see something in the books that I've listed below, and we will make the PDF of this available so people don't need to scramble to write these down. Then I want to give you some sense of that middle of the 19th century. So this is 170 years ago. People knew that things were hanging together in some way, associated. They knew that in acetic acid, there was carbon, oxygen, and hydrogen, but more than that, they knew the proportions of them. But they also got an idea that some groups of atoms hang together, like an O and an H, or a carbon and 3 hydrogens. But they had no good way to represent it. People did not even agree on whether to write the stoichiometric proportions. They knew eventually that in water there were 2, though it took them a long time, that in water there were 2 hydrogens and oxygen, but they didn't know whether to write the 2 as a subscript or a superscript. There was no, and here you see in 5, 6 different representations, I've assembled a collage from the middle of the 19th century. And you see models. For instance, Kekulé, in about 5 years, went through 3 different models, all of which he published on how to represent molecules. For instance, one thing he had was a sausage formula. So at the top, you see the actual model also of a sausage formula for methyl chloride, CH3Cl. So there's a carbon represented by 4 steel balls. Those 4 steel balls are not the atomic weight of carbon. They are the 4 valences of carbon, and 3 of them are used to bond to 3 hydrogens, and 1 is used to bond to a chlorine, and you have to know that the chlorine is not bonded to the hydrogen in that sausage formula. You quickly get used to these. Up at upper right is a formula for acetic acid. You see it? A carbon that's single bonded to a carbon that has 3 hydrogens on the left, double bonded to an oxygen, and then single bonded to an O, which has an H attached to it. Absolutely correct. But you didn't know how to do it. you see the dotted lines. You see in the formula in the middle on the left. Let me see if I can get my pointer going. Hold on for a moment. No, I have my pointer, but I don't have it. I was hoping for a laser pointer, but I don't have it. But you can see this formula, all the parentheses. There were even models. So Hoffmann, August Wilhelm von Hoffmann, no relation to me, had models in 1865, which you see at lower left, which exist to this day, which look just like the models today, except every carbon is square planar and not tetrahedral, because that did not come for another 9 years that one got the three-dimensional picture. Here is fun. This is actually an existing model by Kekule of benzene, of the two, what we would call today the resonance structure of benzene. The four black balls are a carbon. It has a hydrogen, it's single bonded to another carbon, it's double bonded to another carbon. I think you can see that right away. And that goes on around, and these are the two structures. This doesn't have the six-fold symmetry. He knew nothing about six-fold symmetry at that time, except some substitution patterns. The 19th century is a history of development from what were initially called type formulas. Type here means, has its direct transliteration from German. It means that toluene, for instance, had a phenyl group and a methyl group. And the type was the phenyl and the methyl, and they were transferable. So you could also get phenol OH. And as I said, the subscripts, superscripts were not established for a while. It took a good number of years for people to recognize that an OH group of an alcohol could be broken up into an O and an H. And that was then you had the individual types. These were replaced by structural formulas. And so after 1865, you had these formulas that you see here, which look not that different from the modern formulas. And then the Lewis structures interpreted those at the time of the First World War as that a line was really a representation for a shared or unshared electron pair. And then Pauling came along with his reinterpretation of the Heitler-London valence bond theory and reinterpreted those lines as a quantum mechanical shared electron pair with an associate wave function to go with it. The whole story is very interesting from a philosophical point of view. First of all, what you see here is representation. These are people who know that carbon and hydrogen, or whatever the atoms are connected to each other, that they go through the reactions maintaining that connection or trading connections. And they need to represent that going along. And you saw the formulations, how interesting they were in their time. Representation, this is a province of semiotics. Representation is either iconic or symbolic. For instance, an iconic representation is a no smoking sign, okay? A symbolic representation is at the top in what it is in Europe, and at the bottom, the E is there in Brazil. And it really makes a difference when you park there, whether that bar is there or not. Maybe you remember the bar as being iconic, standing for forbidden, but to an American, that European symbol certainly has no meaning whatsoever in its initial symbolism. In the same way, from the beginning in chemistry, there was a mixture of symbolic and iconic representations. The 6 and the 5 in the phenyl group are iconic. They really do stand for weight relationships, and under them are the atomic weights, which began to be formulated from the beginning of the 19th century and pretty well formulated by the middle. The symbols themselves, carbon, oxygen, and hydrogen, of course, are symbolic. Our students learn very quickly that carbon atoms don't have a C painted on them, okay? So they stand for something, but you have to agree on what they stand for. So the whole evolution here is complicated, and what complicates it is something which in philosophy has a name, but it's not generally known, and that is reification. Reification is a fancy word for becoming real in the mind, okay? So you think there is a line between an O and an H in an alcohol. If you ask the chemist in the middle of the 19th century, what does that mean? They would tell you that those are associated with each other. They would make zero speculations about a distance or the strength of the bond or anything else. But with time, my friend Emily Grossholtz, a philosopher and poet, has called reification simply the things become the furniture of the mind. That is, they take a real shape in our minds. And that is what happened with those lines. They became solid. They became lines of some sort. And now there is more, because the further development is not just the idea that they became solid, but it's really a story. It's a fascinating story of how tools and concepts change. It is a story of not of a revolution, but gradual, punctuated evolution. And along the way are appropriation of ideas, that the electron pair was once identified as a line, as a bond, of co-option, of parallel and ambiguous terminologies. This was done in the 19th and 20th century. It was never malicious. It was very human and mostly productive, even as it was confused. Okay, so that's very important for me philosophically in the context of chemistry in general. In terms of philosophies of science, it's not that of Kuhn. It is not quite as chaotic and anarchistic as Paul Feyerabend would have it. Maybe it's very much like Peter Gallison, who has some ideas about how science evolves. I could tell you more about it, but what we have today is a reasonably persistent connection between atoms as a definition of a bond. And boy, does this not satisfy some people, because the words are vague, reasonably persistent, but every word here has meanings, and I'll try to get you some of those meanings by the time we're done. What I'm going to do in the first hour is to tell you about ways of probing bonding experimentally. And in the second hour, I'll tell you about doing it theoretically. And experimentally, we get distances from various methods. We get dissociation energies of the bonds. We get force constants. We can get the density of electrons in a bond. We can probe it magnetically and spectroscopically. And lately, there are techniques of scanning, tunneling microscopy, and atomic force microscopy, of which I'll say some things. We cannot go back in time entirely. So I must start with what we know today. And this is that there is a potential energy, typically for a diatomic molecule, as you see here. And quantum mechanically, there is a potential energy curve with an attraction and then a repulsion. And the motions of the two atoms are quantized. There are molecular vibrations. So there are, and there is a 0-point energy for the vibrations. And there are different ways of defining both the dissociation energy and the force constant, and also the bond length of a molecule, which we are aware of that every method that you use, and chemists learn this more or less well, every method you use to determine any of these experimental quantities is subject to some averaging, which depends on the conditions of the experiment, the time of the experiment, the time scale, and also the temperature, and also the pressure. So on the variation of the physical observables, but we can get at it from this idea of a potential energy curve. So let's talk about distances first. So here is what's happened in the last 50 years, well, actually longer than that. But the evolution, I'll tell you, in the last 50 years. There are machines you can buy, an X-ray diffractometer, which if you have a single crystal, and I'm talking about a discrete molecule, if the molecule cooperates by crystallizing, and a lot of effort is spent on crystallizing, you can get a diffraction pattern, which you see at upper right. And from the diffraction pattern, you can get a map of the electron density, which is sketched at the bottom, not for the same molecule. And then you can get the kind of a picture which you expect to see at lower of a molecule. Here it happens to be an organometallic molecule of nickel with 2 nickel centers in it. The cost of these machines has gone down to of the order of $100,000 or so. And the time with the computer systems that have become available to get the structure has changed from 6 months about 60 years ago when I began research to about a half hour from the time that you take the crystal over, you mount it, to the time that you have the full structure. And it can go quicker than that even. But this is what we have. And I'll tell you in a while how many of these we have. Well, I tell you here. Supposing you want to know the length of a CC bond, and you mean a saturated bond, meaning a single bond, meaning a bond between carbons that are bonded, let's say, to 3 other groups each, and then bonded to each other. So today, if you wanted to know that, it would be a mistake to go to a theoretician. What you need to do is to look in a Cambridge structural database where people have agreed for 60 years to deposit new structures. The database is now a problem because people are not depositing structures anymore. But here is a friend, Jay Siegel, did this just after I talked about this in the seminar, and he said he went into the Cambridge structural database. Here you see how many structures are in there. So let me give you the overall picture. Chemists in 200 years of frenetic activity have characterized about 2 to 3 million about 150 million well-characterized molecules. Well-characterized has to be defined, but they and there's a problem. My DNA is a molecule, your DNA is a molecule, it's a different molecule. Neither is well characterized, but you can get that DNA characterized. Anyway, of those 150 million, about 1.2 million, about 1% have had their crystal structure done. And their coordinates are in a Cambridge structural database, an incredible repository of structural information. And there are about 2,000 neutron structures. There are a few electron diffraction structures. There are a few others, but most of them are X-ray crystallography. So you go into that structure, J. Siegel did, and you ask, give me the compounds that you have, which have 2 carbons, each bonded to 3 other carbons and are bonded to each other. And the crystal structure answers you and says, boy, you don't want to see those because I've got about 17 million such distances. Do you really want to see all of them? Do you have the money to download them? It asks that structure. So Jay said, give me the first 10,000. And that's what you see here. Here you see 10,000, the first 10,000 structures. And what you see is that this, now, what you should know is some of these structures that people have submitted to the Cambridge Structural Database are good ones. Some of them are lousy ones for whatever reason. When you have 1 million of them, it doesn't matter. If you have an intelligent human being, they'll recognize the lousy structures among those as outliers in this game. And so you see that the bond length is 1.53 angstrom. You also see, incidentally, that there are slightly more on the long distance side than there are on the short distance side. That comes from the potential energy curve that you saw. That's not an accident. That's actually some physics being displayed for you. And in fact, the Cambridge Structural Database is an absolutely incredible repository of inspiration for theoreticians because it has facts in there as far as distances are concerned. I could go on for a while now, show you one, but let me show you something more complicated than CC bonds. Here is iodine-iodine bonds. One of the amusing things, the Cambridge Structural Database had a rule from the beginning. They wanted to have organic structures. So they said you have to have 1 carbon, 1 hydrogen in your structure. So the I2 molecule is not in the Cambridge Structural Database. But some I2 molecules are. How did they get in there? That's because they co-crystallize with some organic stuff. And so you've got co-crystals of I2 with some organic molecule. That's the little bond here, 2.66. So what you see here is a wider range of distributions. And what are those various peaks? Well, one of them is I2, which is 2.6. Here's the structure of I2 itself at low temperatures, 2.66 angstrom. Incidentally, if you want to know what is a van der Waals distance, iodine to iodine, don't ask a theoretician. Look in the Cambridge Structural Database. You will see here, for instance, in the I2 structure, which is not in there, it's in another database, you see the next nearest neighbor contacts, so 350 and 427. Those are van der Waals contacts. I'll say in just a moment something more about van der Waals. Many of a big peak in these are I3 minus structures. These are centered at 2.9 angstroms. They're all linear triiodide. There are a few thousand of these structures, and I could tell you about the bonding that's in the second hour. Here is some more of the molecules. There are polyiodides. There is a good review on these. These other structures with intermediate bond lengths here are, usually polyiodides. The big peak here, the first peak is I2 coordinated in various ways. This second peak is triiodides. So there are all kinds of different little bonding things in there. What I want to show you is one of the most creative explorations of the Cambridge Structural Database I know, and what I think is one of the best scientific papers of the last 10 years. This is by Santiago Alvarez in Barcelona, and it's called A Cartography of the Van der Waals Territories. So here is what Alvarez did. He concentrated in his first paper on bonds to oxygen, okay? So he went into the structural database and he asked it for the bond lengths to oxygen of 90 elements of all the things in that database, okay? I show you two of these. This is strontium oxygen, this is rhodium oxygen. Inorganic compounds are going to generate those, but maybe some organometallics as well. So each of these has a peak at low distances, 2.9, 2.4 for these, which are the coordination environments of ionic and organometallic rhodium or strontium oxygen compounds, which are actually bonded to each other in a dative or ionic way. Then you see this rising background here. What are those? Those are non-bonded strontium to oxygen, rhodium to oxygen. So around each oxygen, around each rhodium, there is an oxygen of a coordinated molecule. That's the short distance at 2.3. But further away is some oxygen, which is an alcohol or an aldehyde in some organometallic ligand. And these, they behave, they form, there are many of them. They are occupying a shell of thickness that goes as R squared. You can find how many there are. That's the background that you see here, this line here. That's the distant shell, if you like to think about it, a frozen in solvent shell. And then you see in almost all of them, you see this little peak here. This is not a theoretical result. This is the structures telling you something. They're telling you that there is a distance of 4 angstroms here for this, 4.5 angstroms, which is the Van der Waals distance. It's the non-bonded attraction of a rhodium for an oxygen. And he can get the Van der Waals distances from these graphs. This is an incredible piece of work. It took also a lot of work. I could talk more about it. I could talk about distances forever because I worked with Lipscomb, who was a crystallographer. And one of the things I learned from Professor Lipscomb's group, even though I did not do any crystal structures, I learned how to tell good from bad crystal structures. And I learned also to look at them. I tend to think of myself as a very good observer of crystal structures. And I have gotten a lot of inspiration from them. Okay, we must leave distances, even though they began to be available. As I said, at the time, First World War, we have 1 million structures. We have a lot of information. Let's talk about energies, because from the beginning, the idea of the bond had an associated energy. Now, say you have ethane, CH3, and you want the bond energy So you might think that the easiest and most direct way to get the bond energy is to heat ethane and to see at what point it breaks up into two methyl radicals for the CC bond, and ethyl and the hydrogen for the CH bond. You want both of those. I want both of those. Well, the trouble is that if there are several ways of breaking up, the way that thermal heating works is the weakest bond breaks first. And there is an equilibration of energy among the other things. So it's impossible to get the CH bond energy by heating up ethane. What you can get is the CC bond energy, which turns out to be about 90 kilocalories, or about 4 eV per bond. So in the intervening period, people have perfected ways of getting other bond energies other than the only one available in a complex molecule by simple thermolysis. And they've gotten this by using Bornmeyer cycles and involving both, very often, photoionization mass spectrometry. This is how it works. Let me show you one example. Here is ethane. And my goal is to get the CH bond energy of ethane. There is a review here. So what you do is you shine light on ethane. The light is in a vacuum UV. This is not visible light. Ethane is colorless. And at some point in the UV, there is a threshold for ethane actually absorbing the light and breaking up. And when it breaks up, it goes to ethyl cation and a hydrogen and an electron. It's a photoionization. Now, you can measure that very precisely. You can also independently measure the ionization potential of an ethyl radical, CH3, CH2 neutral. Or you can measure the electron attachment. You can generate the ethyl cation in a molecular beam and measure the energy that's released when an electron is taken up by that ethyl cation. That's the reverse of the ionization potential. So you have a check actually from two directions, but you can get this. Now, if you take these two equations, you just add them up, you get what you want, which is remarkably that you can get the CH bond energy. This is how most bond energies today have been determined. Some are easy, predictable, and they can also be calculated today. And there is an interesting story about modern thermochemical tables are often a combination of experimental and theoretical work. And that's another story. Anyway, a CC bond in ethane of 88 kilocalories is weaker than the energy when two CH2s come together because of the double bond. There are some surprises which are lots of fun to think about. For instance, that same energy for silicon, down group 14, is very different. The gain in a silicon-silicon double bond is not very stable, neither thermodynamically nor kinetically. And there is a story here that's related to the silicon analog of graphene and why that never will be found for freestanding. So there are other things. Silicon is weird and it's not carbon. So this points to me, silicon is my favorite element not because I've done much about it, but because to me, it is the prima facie definition of what is the value of the periodic table. it is the same and not the same. Silicon is like carbon, but it's not like carbon. Here you see it's not like carbon at all. And that's what's interesting. Bond dissociation energies usually correlate with bond distances in the direction that short bonds are strong, of course. And that has been there from the beginning, but it's not always true. Here are some computed, very good computations, potential energy surfaces for the C2 molecule, which I'm interested in here, not because it has a quadruple bond in the ground state or not, but what I'm interested in is in looking just at the ground and excited states and seeing that, in fact, most bonds that are longer equilibrium bond lengths, that's the bottom of these curves, are in fact weaker. But it's not always true. Look at this one over here. That's an excited state of C2 that has a lower bond energy. That's the energy necessary to knock it apart to two carbon atoms. Lower bond energy than the ground state, but has a shorter bond. Isn't that interesting? And I want to know why. Of course, that's why I look at these things. Let's talk about the third measure of bonds, and that is the force constant. So this came also from the beginning, but the general idea is that near the bottom of these potential energy curves for any molecule, you can usually fit a quadratic. Usually, not always. And it's interesting, the cases where you can't are interesting. And that quadratic, there is a force constant. This is the force constant of the spring that gives that molecular vibration. So this is the idea of two atoms connected by a spring and the force constant of that spring. They're of course related, that the force constant goes as the square of the frequency. They're related to each other by a square root along there. There is a reduced mass also. Now, this is behind the use of infrared spectra by organic chemists for 70, 80 years now. This is a typical spectrum of, as it happens, isopropanol. And here, for instance, is an OH stretch characteristic. Also, its shape is very interesting. These things have come of prominence. You know, vibrational spectra are even known to the physics community. I'm joking. But what I'm talking about here is that if you look at the information coming in from outer space, this is from the cloud in Sagittarius. You get, if you look at it at sufficient resolution, you will get spectra that look like the two middle panels here. There are thousands, if not millions, of lines in these. And you look at higher resolution up at the top, and it's still higher resolution over here. And you can see still many, many lines. So what you have is lots of chemistry going on in these clouds or in the atmospheres, the outer flares and atmospheres, especially of brown giants. And people are very interested in these things. Anyway, early on, people tried to calculate, to relate the strength of the bonds to the force constants in such what was called a vibrational analysis. So in a vibrational analysis, what one does is one takes a molecule and one assumes certain force constants for certain bonds, like a CC, CH, and then calculates the vibrations and compares the vibrations with experiment, which you saw on a previous slide, and then gets the force constants which best match the vibrations. This is a grossly underdetermined set of things. it's very interesting to see people talk about this honestly. These vibrational force fields, I should say, have not been so popular. So I had to go back 50 years to find one to show you. This molecule was made, trimethylene methane iron tricarbonyl, a very interesting molecule with threefold symmetry with a C with 3 CH2s above an iron tricarbonyl. The structure was known from an X-ray structure, but someone did a force constant analysis from the detailed measurement of the vibrations. Actually, what happened was two groups did this identical force field analysis. Now, this is just a little sidebar about when two experimental groups study the same thing, and they really are two different groups. This is, and they publish it, as you see here. This is not a good thing for the second one to publishes, but it's the best thing in the world that could happen for the community of chemistry, because it is only when two groups with their own suppositions and different equipment and different attitudes, only when two groups think that they are doing the same thing, that you get a real estimate of what experimental error means. Oh, they can all do the statistics. They all know the statistics. That's not what I'm talking about. I'm talking about the reality of the systematic errors that are hidden, that are not in their statistics. And so this was actually a very good thing. And the two groups got the force constants. These are these Ks for these, another group and them, and many of them differed by 2-3%, but some differed even in sign and were different in substantially. And so one of these was a very honest person. Foyle Miller was a great spectroscopist, and he said, and I want to show this to you, he said 2 different valence force fields are now available for this molecule, that of the other paper and ours. Both reproduce discarding frequencies well, but they differ considerably. Is either set right? We believe that most force constants which have been derived from large symmetry blocks should be regarded with skepticism. And then he traces out the uncertainty. He said the different sets will reproduce the frequencies equally well, and sometimes there are 2 or more sets which seem equally reasonable. It is then almost impossible to tell which is right. One is seldom aware of the existence of these other sets. Big kudos to Foyle Miller for having the courage to say that, and you wish more people would do that. Okay, this triple correlation.
Professor Rhodes.
Yes.
There is a question for you.
Yes.
Berto Lucia is asking, molecular interaction or bond, as he said, is important for energy levels?
Yes.
Okay.
Yes, molecular interaction of bonds. Is it important for the energy levels? I'm not entirely sure what this means. So let's see. Your question presupposes that you start with a localized orbital, with a localized bond orbital picture. And if you do that, yes, that is not a very good starting point for some things. But if you start with localized orbitals, then the interaction of bonds with each other is important for the energy of a molecule. Most of the time, the problem is seen in another way, given that calculations are so easy. Now, most of the time today, one does the calculation in a very delocalized way, then transforms to localized orbitals. And then people fight with each other whether my localization scheme is better than your localization scheme. That's a brief summary of the literature that's out there. By the end of the seminar, the reason they fight will become clear. Please interrupt me again, just like you did. That's good, because I am so drunk on my lecturing that I don't see the chat picture. So I have to.
You.
Okay.
Okay.
This triple correlation of distances, force constants, and energies is called Badger's rule. It is usually valid, but with some exceptions. So that's all that I'll say. Sometimes it fails. Just be aware that this happens. Now let's switch to electron density. So yes, those are available theoretically, but I'm actually talking about experimental electron densities. Today, from low temperature X-ray diffraction experiments, it is possible to get the electron densities in a molecule experimentally. Here, for a molecule, methylcarbamide, Phil Coppens, who is no longer alive, but was one of the best crystallographers we had. Please ignore the black lines and the blue lines too. Just look at the red lines if you can. Those are the actual electron densities in this molecule and their contours. But actually, I want to go to something simpler to show you the trouble with these. Here is BF3. BF3 is a nice molecule with D3H symmetry. Here is a plot from a very good calculation, which should be matched by experiment, of the electron density in the plane of the boron 3 fluorines at left, and in a plane perpendicular to that one that includes a BF bond at right. And what you see is the region of the bond is a minimum of the electron density, not a maximum. So this is where the furniture of the mind has led you astray. This is where 100 years of seeing a line makes you think there is electron density there. There is, but not nearly as much as we think. So what are the peaks of the electron density from in BF3? They are from the cores, of course, from the 1s levels on boron and fluorine, and from some of the 2s levels on fluorine, which are also, but they are from the 1s. The 1s level has, remember the electron density in the 1s level of hydrogen? It goes to a cusp at the nucleus. That's what these do too, the 1s of boron and fluorine. So a bond is actually not a region of maximum in electron density along the bond direction, B to F. But it is a maximum in two planes which are at right angles to that. In the plane that is at right angles to that plane. If I were to draw a plane this way, that would be going across this way. The electron density does rise in the middle. This is we'll come back to this when we talk about quantum theory of atoms and molecules in the second part. But what this means is that getting at the bonding electron density, once you realize that there isn't that much density to worry about, there is some, but there isn't that much in the bond. Getting at the electron density, you think it might be simple. So what you do if you want the electron density of in an H2 bond is you take the calculated or experimental, calculated actually in this case, electron density, and you subtract from it. So now, what do you subtract from it? So the most obvious thing is to subtract spherical atoms. It's what I would do as the first thing. And when you do that for H2, you get the solid lines mean the buildup of electron density. The dashed lines mean a depletion of electron density. The integrated sum of this, of the increases and the depletions is 0. That is, it's just H2. And you're subtracting 2 neutral atoms. And you clearly see a buildup in the region of the bond. And now you do this for F2 with the world's best calculation on F2. And what you find is that in the region of the bond, if you subtract spherical fluorine atoms, in the region of the bond, there is a depletion of electron density. Now that bond is not strong. It's actually 35 kilocalories only. It's not strong, but it's there. And where the electron density piles up is in the regions where a chemist would say the lone pairs are. It's bizarre. But what's wrong here is you have not polarized the atoms to prepare them for bonding. And fluorine is, yes, it's 2s2, 2p5. That's the fluorine atom. But prepared for bonding, it's closer to the chemical picture of having one hybrid toward the center, the configuration which most enters into bonding is a 2p5 configuration that's not spherically symmetrized, but which is depleted in electrons along the axis so that it can form the bond. Okay, W.H.E. Schwartz has analyzed this in some detail. The upshot of the story is, it all makes sense, but you've got to subtract something that's prepared for bonding. And how do you know what's prepared for bonding? By knowing the final bonding. So there is a real circularity built into the system over here. Okay, magnetism, ionization potential, spectroscopy. I don't have too much time, but magnetic criteria in general have been used for analyzing especially weak bonds and especially for inorganic compounds. So the general picture is like this. It's easy to understand. The general picture of this is true for both magnetic and spectroscopic criteria of weak bonding. Here's an example where this is analyzed. This is 2 copper atoms with 4 acetates bridging the copper atoms. You see here as bidentate ligands. And then there's a water at the end and at the top and the bottom. That copper is a copper plus 2. Copper plus 2 has got a hole in the D block. And so there is an odd electron in here, actually in an orbital, a d orbital that's pointing toward the ligands, and there is an odd electron in a copper underneath. The 2 coppers are separated experimentally by a distance that is 2.75 angstroms, just a bit longer than a single bond. Is there a bond between the 2 coppers? That's the question. Typical inorganic bonding question. It can be often translated into a more complicated question of, is the ground state of the molecule high spin or low spin? That's what I'm asking now. Are the 2 electrons unpaired, high spin, or are they paired, low spin? It also translates in a solid state in the question of ferromagnetic or antiferromagnetic coupling. The general picture is like this. There is a bond and an antibond. Call those a sigma and sigma star. There are two electrons to be put in there. If the two orbitals are not far from each other, that's what weak bonding means. If the two orbitals are not far, if they're far from each other, you've got a strong bond. There is no question the ground state is a singlet. No one would propose a high spin molecule for a strong bond. But when your two levels are close to each other, then there are four configurations that compete for being the ground state. One of them a triplet and three singlets, 6 microstates. And if the two levels are very close to each other, usually the triplet wins out and is the ground state. But this is the basic question, and this is how this orbital splittings and the values of the exchange integrals that are involved here. I'm using theoretical language, but the simple theory behind this, I've essentially said in words, is there and it's used in magnetic criteria. Spectroscopic measures of weak bonding are similar. If you have a bond that is a bonding and antibonding orbital, 2 electrons in it, and then if you somehow increase the strength of the bonding, which means split the bonding and antibonding levels apart more, you will get a blue shift of the first electronic transition, which is promoting one electron to the other level. And this is, I am not doing justice to this. In my own work, I've done this because I want to finish the first part. And that comes with my talking about STM. STM, scanning tunneling microscopy, an incredible technique coming out from the mid-90s, where you take a tip, typically it was tungsten in the beginning, and you can maneuver that tip relative to a conducting surface, and you could put a molecule on it, and you measure the tunneling current through whatever molecules on top of this, or just from the surface. And you have exquisite control to angstrom, 10th of an angstrom scale in all 3 dimensions, in jamming it into the surface and in laterally moving it along the surface. And the first pictures were incredible of an unusual reconstruction on a surface of silicon called a silicon 111 surface. Because this was done at IBM, from the beginning, there was an extraordinary amount of hype attached to this because it was done at a company. Not that scientists working for themselves are incapable of generating hype. They are, helped by the public affairs office of their universities. But in this case, a company, IBM, did it. And so what the advertising typically said is, now, after 2,000 years of waiting, you can finally see atoms. Well, I went through the ceiling when I heard that, because that scanning tunneling microscope would not have been built if it were not for 200 years of chemistry, which worked hard and combined the fallible experiments, our tools, with our equally fallible minds in an social activity called science, in order to gain not deniable evidence of how atoms were connected to each other. I'll show you, we didn't need the STM to know the structure of a molecule. And for God's sakes, give proper credit where it's due, and that is to knowing without seeing, okay? That's in a way what we did. That doesn't mean we didn't do science, but we just didn't see the atoms, but we knew they were there. I think that's much more interesting than seeing them. I also think that knowing without seeing is an important bridge between science and the humanities. This is another story I talk about. So what's the situation now, 25 years after this development? Situation is sort of like this. Here is a model at lower left of a phthalocyanine molecule in a crystal, 4 of them. And what you see is in the STM today is something like this. You don't have, in the STM pictures, you don't have very good resolution. Actually, what you see in the STM is something in a way much more interesting than the atoms, because what you are observing is a tunneling current, and you set the bias of the tip from the plate underneath. So you can tunnel out of filled levels of whatever molecules on the plate. Or there is a certain inverse experiment where you can actually probe unfilled levels of the molecule on there. And so what you see here at lower right is the pentacene molecule in an STM. And this is with a bias set about 2 or something, 2 to 3 EV below the Fermi level, below the level of conductivity. So what you are seeing here is contours of the electron density from the molecular orbital, which is occupied, which is not the HOMO, not the highest occupied molecular orbital, but some lower molecular orbital. You can go through the molecular orbitals and get a plot of psi squared of a molecule, and that's very interesting. Now, things have happened since then. Atomic force microscopy has developed stronger, and it often today has something else at the tip. And one of the things they've gotten on the tip that's proven very useful is a carbon monoxide molecule. They pick it up from the surface and then they move over and they sweep it over a pentacene molecule. And you get, what you get is actually a repulsion, a map of the repulsion of the oxygen for the atoms underneath. You get a picture of that repulsion like this, and then you massage it through some programs to get the picture that you see at the bottom. And these are the pictures that are published. They are bright in some parts, and it certainly looks like the molecule that you know it is. And you can run even a set of reactions with this. Here is a remarkable paper from 2016 where dibromoanthracene, here you see anthracene with these weird lining up of the ends, 2 bromines here, and then one bromine is pushed off and you can actually see the radical. This is incredible, incredible in some way. And then you see the diradical with both bromines off. And then you see a rearrangement, actually an electrocyclic opening of a polyene to give another ring. When you see this, you are just full of wonder what you get until you start asking the question, and that is, what are you seeing actually? It is not a map of the electron density, but it's something related. And I'm not sure to this day I understand what I'm seeing, though I've tried very hard to understand. And if someone shows you these pictures in a seminar, please ask, what are you measuring? Because it is actually very interesting. Now, I just want to be sure. This here is a picture of pentacene in the middle, obtained from atomic force microscopy and worth 3 papers in Science and Nature, okay, in 2016 to 2020. Down at the bottom is the X-ray crystal structure of pentacene from a paper in 1949, which gives you slightly more significant figures than are permissible here really by the experiment, but which gives you the metrics of the molecule. So which is worth more to you? I think it's pretty clear. The crystal structure gives you more metric information on this. We are at the end of my first part. I just want to leave with you while we have an intermission, this picture, a detail from Raphael's fresco in the Vatican Library, the school of philosophers as Plato and Aristotle in the middle. And he could not be sure that even his learned audience of priests in the Vatican Library would know who was Plato and who was Aristotle. So he gives each other a book, and you can read that Aristotle is Ithaca, and Plato has here, I think it's Timaeus over here, so they would know who is who by their books they have written. And you see here, up there, that's Plato pointing to the ideal forms that are the underlying reality. Down here is Aristotle. We think of Aristotle having led physics astray. He didn't lead physics astray. He was a very careful observer of nature, remarkable observations for his time. But to me, Aristotle here stands for experiment and Plato for theory up there. So we better go, and after a break for 5 minutes, we will be back, okay?
Okay, Professor, but before that, there is another question for you.
Yes.
They are asking, it's about carbon and silicon. How would symmetry affect the bonds between carbon and silicon and their electron density?
Indirectly, the effect of symmetry. So the story very briefly can be traced. The story has to do with the instability of pi bonding in silicon. The sigma bonding is okay, as we can see from that bond strength. Also, silicon has an extraordinary bond strength to oxygen, and that more stronger than carbon, which is also strong. So the silicon-oxygen bonding is especially strong. The symmetry, I would tend to say affects it only indirectly. It has more to do with the difference in energy between 3s and 3p of silicon relative to 2s and 2p of carbon. And then it has to do with the overlaps between two silicon atoms, between the relative strengths of 2s, 2s, and 2s, 2p sigma overlaps of the atoms with each other. Those are, to me, the main qualitative factors that govern this.
Okay.
Okay, we stop for 5 minutes?
Yes. Thank you. George? Okay, Professor, go ahead, please.
Okay. So I want to tell you about a limited number of ways of analyzing bonding theoretically. And just like in the experimental work, I will not be able to do justice to some of these methods, but I will cover a good part of what's out there: molecular orbitals, bond orders, beta analysis, QTAIM, electron localization functions, natural bond orbitals, energy partitioning, and then make some special comments.
Professor, before you start, can I ask a question?
Yes, of course.
Yes, there is one here. Does the higher light intensity observed at the sides of pentacene have any meaning regarding an electronic picture of its surface?
The answer is no. It has no chemical meaning. And I don't know why it is higher, that light, those light up pictures. I just don't. Here they are. And I don't know why it's higher. And I cannot get a satisfactory answer from the people who do it. So you ask them. It looks like the molecule for sure. I think that part of it's something to do with the program, but I think part of the story has to do with the carbon monoxide tip repelling the electron density, but also bending as it passes over the molecule to stay away from the electron density. And I somehow, when it is at the end of the molecule, it doesn't have to bend away so much. I don't know how else to say it. I try to understand it, but I don't. So perhaps if one of you finds a good explanation, let me know about it too. I mean, when one sees something like what I just showed you, that's just incredible. But I tell you, I haven't seen anything better in the last few years. So the improvements were still at that point. Okay. So, but before I begin my theoretical story, and I want to show you something. So in 1913, Niels Bohr published his old quantum theory, which involved a quantization of angular momentum and derived the formula for the levels of the hydrogen atom correctly. This was the beginning of the old quantum theory, which lasted all of 13 years, but the impact was incredible. Niels Bohr knew some chemistry from his brother, and who was a biologist and chemist, and also he had learned some. So he actually thought at that time, while he was writing his 1913 paper, he thought that he could extend his reasoning to molecules. And what I show you from a paper that was published in 2005 is a page from some notes that a model that Niels Bohr put into a manuscript that was never published about his ideas for molecules. So here is Niels Bohr's idea for H2 molecule. He put 2 electrons. Remember the Bohr model had an orbit, which was circular orbits. He put them in a circular orbit around the center of the molecule. H2O, he actually knew that water was bent, but he put the inner core electrons of the oxygen in an orbit around the oxygen nucleus, and then he put 2 electrons for the OH bonds at the center of the OH bonds. O2 gave him some trouble. It gave valence bond theory troubles too. O3, he actually drew for O3 what we would today call 2 resonance structures. A double bond here with 4 electrons shared with these 2 oxygens and 2 electrons shared between these 2. And then he drew a double 3 electron bond. These are all anticipating valence bond structures. He even knew that methane was tetrahedral. You see here his attempt to draw a tetrahedral methane, and with 2 CH bonds and acetylene too. So this is pretty incredible. It's sort of fun to see this. We could have had this, but we didn't. Okay. Back to MO theory. 2 orbitals interacting, chi1 and chi2. This is simple MO theory. They interact with each other. If you like, this is perturbation theory at work. They mix with each other, and you get resultant wave functions psi1, which has mostly chi1 on the left and mixes in some of chi2 on the right in a bonding way. Shading means plus, no shading means minus. Okay, do I have to tell you why I don't use plus and minus? The reason that I wanted to do that, I don't use plus and minus, is that I want you to understand that the absolute phase of the wave function is unimportant. It's the relative phase. So when you see shading, that can mean plus on Mondays, Wednesdays, and Fridays, and on Tuesdays, Thursdays, and Saturdays, it means minus and is an imaginary number on Sunday. So it doesn't matter. A bonding orbital is bonding because plus goes with plus or minus with minus. Doesn't matter. And an anti-bonding orbital, the high one, is plus with minus or minus with plus. Okay. 2 levels interacting, mixing interaction. Somehow how to quantify the bonding that comes. And now it matters how many electrons you put in there, because if you put 2 electrons in, that's at lower left here, then you have bonding overall. But if you put 4 electrons in, that's a model for helium-2, for instance, then you get net anti-bonding, because as it happens, the higher combination goes up more than the lower combination once the overlap is included. Anyway, these are how to quantify that bonding. Now, you can do more complicated things. Here's what we do with high school students at a good high school, Liceo in Brazil or the United States, for a diatomic molecule, but if not, at the university, you interact, let's say you're building a nitrogen molecule for 2 nitrogen atoms, you interact the 2s and 2p, you get in-phase and out-of-phase combinations. For the 2p's, there is a sigma interaction. You judge that the sigma overlap is bigger than the pi. This is where the carbon-silicon stories differ a little bit. So that splitting is more here, more interaction, whereas the pi splitting is less, a little bit less. And here are the orbitals at the 0th level. Now this is high school and beginning university. This is a graduate course in quantum mechanics, quantum chemistry, because what you have at left is just the beginning. What you have done, let me say it technically for those of you who are aware. What I've done at left is done 0th order degenerate perturbation theory. Degenerate because S is degenerate with S and P degenerate with P. 0th order because when you do perturbation theory, what you do first is set up little 2x2 or 6x6 matrices for the degenerate orbitals, and you prepare the orbitals for the perturbation by diagonalizing those matrices. But then in the next stage, what you do is you turn on other interactions. This is really 0th order perturbation theory. And the next interaction is that this sigma G here, there is another sigma G right above it. Look at that. And this sigma U here has another sigma U up above it. The pi orbitals are just fine like they are. But the sigma orbitals have other orbitals. And one of the rules of perturbation theory is, reduced to simple words, is if anything can mix, it will. It's just a question of how much. How much depends on overlap and inversely by the difference in energy between the interacting orbitals. So two orbitals which are close to each other interact more than two orbitals that are far apart from each other. That's all. Then there's over. So this orbital here mixes with the one above it, 2 sigma G. They're of the same symmetry. They can interact. They don't interact with sigma U orbitals. Those are different symmetry. That's where symmetry. Symmetry is usually rationalized to our students as being worth studying because how elegant and simple it is. But really, there is a much more basic human emotion that should be behind learning group theory, and that is laziness. Anything that you can do with group theory, you can do without group theory with more work. So when I tell you that sigma G does not interact with sigma U, supposing you don't believe me, so you calculate the overlap integral and you'd find it's 0. Symmetry tells you it's 0 right away. Okay. Anyway, these two sigma G orbitals interact to give a stronger bond and a lone pair combination, pointing out. You cannot make two strong bonds out of two orbitals interacting. If one goes up, the other one, if one goes down, the other one goes up. Similarly, the sigma U here, sorry, I said this interacts with this one. I said it wrong. Let me start again. The sigma G on the left and the sigma G on the right interact to give the 1 sigma G and 2 sigma G on the right. The sigma U here interacts with its partner way up to give one combination here and one here. And this is the way that in MO theory, if you go to second order in the interactions, that's what we're doing. We're doing second order interaction. What you get is not the simplistic picture at the left, but you get bonds and lone pairs out. That's very chemical, very chemical. And that's why it's important to do this. Okay, how to analyze the amount of bonding. And I look at these MOs. The next thing I want is some measure of the bonding in these. Okay, this is the ones at left, it's clear. That's bonding, that's anti-bonding, bonding, and so on. That world is too simplistic a world. it's the high school world. We'll talk again about teaching. The real world has, this is a very bonding orbital. This is a slightly anti-bonding orbital. This is a bonding orbital. This is a slightly bonding orbital, and so on. I want to quantify, if I have a method, these things. So Mulliken faced this and devised a bond index. So what we're talking about is strengths of bonds as measured from calculations. And the generic word I will use are bond indices. There are various kinds of bond indices. They just indicate quantitative. So Mulliken did it this way. He said, if you have a bond, if you have two orbitals which mix, the orbital has to be normalized. Any self-respecting MO has to be normalized. So if the orbitals are individually normalized, the integral phi 1 squared is just 1. The integral phi 2 squared by itself is 1. So this comes out to be, if you take 1, the normalization of the MO, it's C1 squared plus C2 squared plus 2, C1, C2, integral of phi1, phi2. Integral phi1, phi2 means the overlap integral between these two. So obviously, if there is no bonding, obviously this last thing has something to do with the bonding. And these two don't. They're individual to the atoms, at least in a simple picture. So he decided to call an overlap population 2C1C2S12. So what do you want a bond index to be? So here, even without starting out, what you want a bond index to be is positive when there is a bond, negative when there is anti-bonding, and 0 when there isn't much bonding. The demands are not great, but they're at least that, okay? So if you have both of these positive and the overlap is positive and large, then you have bonding. If your electrons were instead in this orbital at the top, that would be a plus times a minus, and the overlap would be positive still. So plus times plus would give a minus. So that would give you a negative index. And so this bond index of Mulliken, called an overlap population, is large if you have large coefficients. That means a lot of mixing. And you must have overlap. Why is that important? Here is something that no chemist would imagine would have a large contribution to a bond strength, even though the coefficients are large. Take the combinations that you are forced to take of the 1s orbitals on carbon in ethane. The 1s orbitals on carbon are 400 eV below ionization. They are very tight around the carbon. They have, but yet when you form MOs of the 1s's, this is not chemistry. This is not valence orbitals. This is inner cores. If you form the plus and the minus of the core, you have equal coefficients. But the overlap between the cores is close to 0 because they're so tight. So this is not a bad bond index, but it has some problems. We realized that right away. Mulliken realized it. And people have devised other bond indices. Just the fact that you, in the literature, when you read papers, can see that some people use Weiberg bond indices, Meyer or Levdine ones. What that tells you is that no one can agree on what is the best bond index. That's what it tells you. that they give it different names. Of course, everyone has its advantages and disadvantages. These bond index values are not 1, 2, 3. So go back to this. In the world, which is the high school world, the bond index for this 2 electrons lower MO is 1. For this one is -1. For this one, 1. 1 for each of the 2 electrons. But the real ones are something like 0. Something like bigger than 1 for this one, less than 1 for this one, and so on. So they're not exactly what the chemists want them to be, but they're there. You can still, I don't have time to tell you about this. It's an interesting story. I'll just show you the structure. The beauty of chemistry is the molecules we make. So I cannot pass up a structure to show you, even though the bonding analysis is tight. So here is a set of compounds, which are 2 golds, a metal, and 2 phosphines, with the metal being lead, thallium, or mercury, made by Eschen and Yaichko. And the structures are with phosphorus with small black circles. The large black circles with the numbers are golds, and the white circles here are lead, thallium, or mercury. So now just look overall at the structure. What you see are approximate cubes of phosphorus and lead, of phosphorus and gold atoms around a line of lead, thallium, or mercury running through it like a needle. I didn't tell you the distances, but remember, I'm a consumer of Cambridge Structural Database. The distances are 320, 319, 316. Those look rather large, but actually a mercury-mercury distance in metallic mercury is not much larger than that. So that these are actually, and thallium and lead, those are big atoms, mercury, thallium, and lead. These distances are in a range of weak bonds. So let me now translate this into English, which turns out to be the same as Portuguese here. In these structures, there are quasi one-dimensional needles of lead, thallium, or mercury. That's pretty interesting. We're always interested in one-dimensional solids, and they are there. They're running through this, and the distances indicate partial bonding. And there's a difference, of course, between lead, thallium, and mercury. There's a difference of these are, I've forgotten what the principal quantum number, but the lead has 4 valence electrons, thallium 3, and mercury 2. So these are not only, they're the same structure by different electron count. When I see that, I sit up. The same structure, but different electron count. That's like nature. That's like PV equals nRT. And here is nature allowing me just to vary V, or just allow it to vary. It's varying one parameter, and I'm interested in it. Okay, I'm going to leave that for now and leave it for you. Let's talk about atoms and molecules. This has been a popular way, popularized by Richard Bader, who started out as an organic chemist, but then turned out to be a superb theoretician, did many important things, and he's written about this widely. And what it has to do with is, by now you've forgotten, but BF3, when you remember the electron density in that, I want to remind you that the electron density was a minimum along the bond line. but a maximum in 2 directions perpendicular to the bond line. So that's what's called -1, 1, 1. There's a critical point of a certain type. And when you plot the electron density, and then you plot the electron density in a certain plane, and then you plot out the gradient of the electron density. I don't have the electron. Here it is. Here. Remember the red lines are the electron density for this molecule? Okay. The blue lines are the gradient. The gradient is the derivative of the electron density. It's nothing fancy. It's just the derivative. It has a direction, but here are contours of the gradient. It turns out that the contours of the gradient terminate at atoms and then go to 0 at a unique line, a unique surface, which here appears as a line in this 2-dimensional cut, but it's really a surface. And that electron density, the gradient, that means how it changes, is such that this point, that there is a point in between the B and the F, which is a minimum with respect, these are the arrows indicate the direction of the gradient, that it's increasing in that direction, okay? So it's increasing, the thing is a 0 here, and then it increases the electron density toward, not a 0, it's a finite value, toward the atoms, and it decreases in a perpendicular direction. Richard Bader called the existence of such points, called this line that comes between atoms. He called this a bond critical point. And these basins, which are defined by the surfaces of 0 gradient, he called atomic basins. It divides space into all basins, but I want you to see right away here. So, and now, let me now backtrack a little bit. This was an experimental electron density. You can do this analysis on an experimental one. You can do it on a theoretical one. The world of the is divided into basins, which are defined by these dark lines. What you're seeing is a line because we've taken a 2-dimensional cut. That line is actually a surface in 3 dimensions. So the carbon atom here is not a little ball. Yes, the inner core is a little ball around carbon, but not the carbon atom of the quantum theory atoms molecule. Carbon atom quantum theory atom molecules is a piece of space that goes out to infinity. That is there. And that carbon atom here, however, is a piece of which is in some weird area that looks in no way like a sphere. So the basins don't look like the space-filling model building blocks of atoms, but it's okay. So they don't have to look the way your prejudices are. The hydrogens are going out to infinity too. Weird, but okay. But along the line between each of the atoms, there is a line where the density, the gradient goes to 0 here. The density decreases along that line, and perpendicular to that line, the density increases. These define the basins, they define charges also, and they define something like which he calls bond critical points. These are the bond critical points. Those are the points which is the minimum of the electron density, but a maximum in 2 other dimensions. Okay, he says that's what defines a bond. So this looks okay. It's a little, look at this picture again. Now I want you to look at the lines. This is the lines, the little black lines, which are hard to see, are what the quantum theory of atoms and molecules tells you the bonds are. Those lines, those are bond paths. Notice there is no bond line from that oxygen to that carbon. There is no line here. There is a line from that oxygen only to the carbon. It looks at this point like everything's making sense. But it gets into trouble. Well, so here is a picture, for instance, of phenanthrene and biphenyl. And in these pictures, the red dot, this shows the bond paths, which are the yellow lines. The bond critical point is the little red point. And what you see is everything in most of the molecule is exactly as you imagine it should be, except between those 2 hydrogens, there is a bond path. And there is a bond critical point between the 2 hydrogens. The same between biphenyl, those 2 hydrogens, in a planar conformation. That is in trouble because every organic chemist knows that those positions of on a phenanthrene and those positions on a biphenyl are sterically hindered. Okay, so what the heck does the chemist mean by sterically hindered? So I'll tell you what they mean. They mean that if I put methyl groups instead of hydrogens there, I have trouble putting them in. And there are signs that the methyl groups repel each other in the crystal structure. And I cannot put 2 T-butyl groups there. That is, the chemist translates that into the thing that the organic chemist is a master of doing, which is of making molecules. The same over here. If you put bulky groups over here, they move away from each other. So Bader's mistake was he tried to get out of this by postulating an attraction between those hydrogens, and that it's just not there in a sense that we normally think about it. No chemical consequences. Here is the real sort of reductio ad absurdum, which made people wonder. This is Buckminster fullerene, a wonderful molecule, stable as a rock. Here's a bond critical point at the midpoint of every CC bond of the molecule. And this is a helium atom trapped in C60. Now, it turns out you can make this. You make this by heating the hell out of Buckminster fullerene in a helium atmosphere. And in pops a helium and the cage closes up again. You can know it's there by doing a helium isotope NMR on it. So actually, one knows this is there aside from the mass spectrum. And when you do a calculation on this, between the helium atom and every one of the 60 carbons of the Buckminster fullerene is a bond path and a bond critical point. Now, you can make a story around here, but telling a chemist that there are 60 helium carbon bonds here is not going to sell. This index has no chemical sense. And it's in fact a consequence just of the topology. Now, there are things that you find that there are other indicators. It turns out that if you look at the second derivative of the electron density, the Laplacian, then that measures the balance between kinetic and potential energy densities at the bond critical point. And when this is negative, one typically has a covalent bond. And positive L, which is what would happen for that helium and C60, you would get your repulsion. There are other measures which are a little bit better, but the simple bond analysis is a problem. Okay, now I'll say something more in just a moment. Let me talk about electron localization function. The electron localization function, due to Becker and Edgecombe about 30 years ago, is a measure. It's something which is based on a very good idea. The very good idea is that the basic characteristic of a bond is that there are two electrons in it of opposite spin. So what they wanted was to find a measure of places in the molecule where there are two electrons of opposite spin. Turns out that it's difficult to calculate that. So they instead focused on something different, which is they made the supposition that the place where there's a lot of electrons of opposite spin will be places where there is little electrons of the same spin. And so turns out that's easier to calculate. It's not that easy for some things, but easier. And they then devised a measure which was designed to go between 0 and 1. The 0, this form of this is only to make it come out between 0 and 1. Don't worry about the form. But into it goes an f of r. This f of r is complicated. It's the curvature, which means the second derivative, of the pair probability function of electrons of the same spin. And then it had to be made relative to something. So they made it relative to a very unchemical thing and hoped that chemists wouldn't notice. And that is, they made it a free relative to a free electron gas. This has been modified later. But let me translate this into English. F of R is large where you have a lot of electrons of the same spin. A region of space where you have a lot of electrons of the same. F of R is small when you have a small number of this, therefore a large number of this. That's the reason. Okay. Incidentally, if you get in your hand someone who's willing to answer questions while they show you many elves, just ask them innocently, what does elf mean? And you'll see whether they understand or not this. Okay, so they didn't calculate it for some simple molecules. Whenever I see an index, a measure of anything, I'm a chemist. I'm a chemist hiding as a theoretician. I'm a chemist. So I know how things are. When somebody's going to show me some index of a bond, which tells me that it has a big value when there is a pair of electrons of opposite spin, I think of lone pairs and bonds. That's what I think of. So you might think that they would immediately apply it in their first paper to water and ammonia. No, they're not going to do it. Someone else had to do it. Burdett and McCormick quickly applied this L function to ammonia and water. And here it is for water in upper left and ammonia next to it. And you see these are contours of a high value of ELF, approaching 1. And what you see is a lone pair. The other place where there are high values is in inner cores. A 1s orbital has 2 electrons. The kinetic energy wins out. Here are the 2 lone pairs of water. Here is the 1 lone pair of ammonia. And the weird thing is the CH bonds. The ELF basins for CH bonds look like big balloons. And I don't understand why, but those are the regions where there is a high probability of finding 2 electrons. I understand why you have to go far out, because then the 2 electrons are not squeezed together that are of opposite spin. But why they're so polarized toward the hydrogen, I'm not sure. Next to it here, this will help also. I'm trying to convince you of the normality of ELF, or why it's of value, okay? So this is cyclohexane. I bet you didn't think of cyclohexane this way, but this is cyclohexane. And the little green regions are the CC bonds in ELF. And the blue balloons are each of the hydrogens. Yeah. This is cyclopropane next to it. Look at that. You see the balloons for the hydrogens, and then you see the CC bond region, and before your eyes, you see a bent bond. Just what organic chemists would tell you, that the bonds in cyclopropane are not along the lines, but bent out a little bit. Interesting. Here is acetylene in an ELF map. H, C, C, H. 2 balloons for the hydrogens. We're getting used to those. A torus. What is going on there? So what's happening there, it's not seeing the sigma bond. The sigma bond doesn't localize very well, but the pi bonds are pretty localized. And since the 2 pi bonds are orthogonal to each other, they give a cylinder. That's the torus. That's the pi bond. And the little red areas are the inner cores. So you have to get used to them, but it's not bad. There is recently another indicator called Li, which is the same thing, restricted in the region. Here's an Li for acetylene. Whenever somebody gives you a bond indicator, if it's a matter of pushing a button in a program, the first advice to your students is, for God's sakes, try it out on a molecule, you know what it should come out. Okay, so that's what I'm doing. And this is acetylene, and those hydrogen balloons are weird, but the rest of it I begin to understand. So what shall we do with these 2 theories, ELF and QTAAM? So I've written an article on why people accept theories.
Professor, let me just make a question, please.
Yes.
With those models, is it possible to identify double bonds, triple bonds, or just there is a bond?
Not in these models. You cannot identify the double trick. You cannot identify, as far as I know.
Thank you.
Okay. So why should one accept these theories? I think theories, the usual thing is people accept theories because they explain better or more of what is known. They fit with known theories. We don't expect one theory to work for everything. And also what makes people accept theories is that they make verifiable and preferably risky prediction. What's a risky prediction? A risky prediction is if you convene 90% of, if you convene the experts in the field and 90% of the experts vote that a certain predicted outcome is wrong. If it comes out right, that's a risky theory. That's a risky prediction. That's what happened with Einstein's prediction of the advancement of the perihelion of Mercury. The reasons were not known. There are other reasons why people accept theories, and they are very important. One is aesthetic reasons, and foremost in them is simplicity. So I can say this in a number of ways, but let me try to say it we fall for simplicity every time. Or to put it another way, we think the universe is as simple as our minds are. There are many different ways. And Einstein said it right. He said the universe is as complex as it has to be in order to be what it is. And simplicity and the idea, especially of beautiful equations, is a real danger. Symmetry also is a danger. Why is water bent? Why isn't it linear? Wouldn't the world be nicer if water were linear? Well, it isn't, and so on. There are other reasons why people accept theories. One is they tell a good story. And this is sometimes good, sometimes bad. But the narrative structure of theories is very important. That they form frameworks of understanding, that they can encompass a number of things. A very controversial thing is social needs of a community. The theories reflect things which are not just about facts, but which are about what the world wants, and what the world wants at any time is what it gets. Evelyn Fox Keller, in Making Sense of Life, says this in some detail. Let me summarize it in a sentence. The gentlemen of the Royal Society and the French Academy of Sciences, wonderful scientists, all in 1800, would not believe that a woman, an Asian, a Jew, or a Black would be able to do science. What was their reason for their not thinking this? It was the community around them. And how many other things are still buried in our community, even as we think we have come wider? And of course, they were wrong. There are other things about theory, acceptance of theories. I believe that theories that are portable, that you can give to somebody else, are better accepted than theories which are private or which you require a certain person. This is very hard for theoreticians to understand. That if you give away a theory to somebody, that's what makes your theory valuable. That somebody else can use it. That it's teachable. There are any number of ways to say this. Productive means that it suggests experiments. My personal opinion is that quantum theory of atoms and molecules is beautiful, analytical, and descriptive. It is not predictive nor productive. And as such, it is not inherently chemical and of value to chemists. It is a way of analyzing the electron density. ELF, I think, is a little better. It can lead to some productive insights. And I mentioned the solid state work of Uri Green. I think that's a little bit better, but it's still very unchemical at some level and has to be used with caution along with other things. Okay, I've not left myself enough time for natural bond orbitals and other things. Natural bond orbitals is an analysis due to Weinhold. Again, there's a book on it. There is a complex series of transformations of the wave function to form natural orbitals. And there are several matrix diagonalizations along the way. there are a lot of hidden assumptions. For if there are any organometallic chemists in the audience, one of the hidden assumptions in the application of natural orbitals to inorganic compounds is for transition metals, they begin with a built-in assumption that p orbitals on the metal are somehow not in the basis set. And so at the end of it, they come out that p orbitals are not important in the bonding. So, but I think it's built into the theory in some way. It gives things that are very chemical, and it gives reasonable charges, especially, which is interesting, a little bit exaggerated. Here's example methylamine, CH3NH2, done with Weinhold scheme. You get a lower left, you get a bond orbital for the CN bond, sigma bond. You get an anti-bonding orbital looking just like what you think. This is a contour of electron density. And then you get, to form those bonds, you can form hybrids in this method. There is a hybrid on the nitrogen. There is a hybrid on the carbon. You form this bond from these. It's a very chemical picture. You get a negative charge on the carbon, a positive charge on hydrogen, negative charge on the carbon here, but less than on the nitrogen because some electron density is stolen. The charges seem reasonable, somewhat exaggerated. You see the hydrogens here, they are too positive, I think. It's a very chemical picture. And one interesting thing about it, it has a perturbation theory attached to it. So you can analyze interactions. I would recommend this method in general, but just applies with some caution. Energy decomposition analysis goes back to Murokuma, and then eventually in the hands of Behrens and Pickelhaupt has become formalized in the ADF, the Amsterdam Density Functional Programs, and has been used in a number of ways. Also, Franking has popularized this a lot. Let me show you a little bit from Franking's work. The general idea is simple, and that is that somehow the total energy of a molecule, don't pay any attention to these, in fact, I'm not going to show it. The general idea is that somehow the total energy of the molecule, with all the terms in the Hamiltonian, the kinetic energy, the potential energy, everything else, can be decomposed into atomic compositions, into atomic contributions, and then their interaction. And that decomposition proceeds in several steps, where there's a first step where the fragments of the molecule are prepared for bonding. So if you are trying to calculate how two methyl groups bond in ethane, you first take a CH3 and you distort it to be pyramidal. Okay, that requires certain energy. Then you are prepared. And once you do this, you calculate first the electrostatic interaction of the pluses and minuses over here with the ones on the other atom, quantum mechanically. You then calculate also the Pauli repulsion of the electron densities here for the next one. This is actually the term that's analogous to the 4 electron repulsions in the simplified MO theory. And then you have finally an orbital interaction where filled orbitals of one fragment interact with unfilled orbitals of the other fragment. That's the interaction, that's the orbital part. It's easier to get a feeling for this by seeing what happens. So here is Franking analyzing ethane, ethylene, acetylene by making them from their fragments. 2 CH3s, 2 CH2s, 2 CHs, okay? The interaction energy, here it is, I think, I don't even know what units this is. If it's, I think it's kilojoules. No, it must be kilocalories because the association energy. It's in kilocalories. You see the interaction energy of two CHs is bigger than two C2H4, CH2s than two methyls. Okay, now he analyzes that and he gets the Pauli interaction is always repulsive. The orbitals of electrons in these orbitals always repel the electrons in these orbitals, as if you analyze it in this way, by making the wave function anti-symmetric. The electrostatics is always negative, and the sum of the two is always slightly somewhat positive. And then the orbital interaction, you remember the numbers here initially for the interaction of the two fragments, the energy. There are too many significant figures on all of these numbers. It's terrible. One should teach a course about how theoretical chemists should learn that in the number of significant figures, more is less. Meaning, the more figures you give, the less is someone likely to interpret it. You notice the interaction energies goes minus 100, minus 190, minus 280. They increase in the fragments. The orbital energies are also going like that, increasing by 100 for each, as you see here. And you can partition this into a sigma and pi, and you notice the ethane has no sigma, no pi, but ethylene has 79 kilocalories of a pi, and acetylene has twice as much, not quite, but in that direction. The sigmas, on the other hand, are the same. Let me summarize this for you, and you can check it against your experience. In every case of chemical significance I know, the total energy of interaction goes like the orbital interaction energy in this partitioning. That is what you see up there is the way that this goes. The numbers are different. Usually there's repulsion to lessen the orbital energy, but it's in that direction. Okay, I have now done these things, and it looks like I have come to this situation. That is, I've come to a situation of thoroughly confusing you, except for some strong opinions about QTAAM and ELF, which you can argue with me. And if Richard Bader were alive, he would argue with me very vociferously. But basically, it looks like there are several different ways of interpreting the bonding in these. And I've tried to be fair, but I am driven by my prejudice. So I want to now, even though I've tried to be fair, I think there should be little doubt in your mind about what I believe. And what I believe is that simple orbital interactions can get you most of the way on analyzing bonding. And I will tell you what I mean by that, or try to make a case for that. On this one molecule that I showed you before, C2, here are all these potential energy curves. And we know the ground state, and there's a big debate, as you have seen, on whether this ground state, with its bond lengths of 1.24, that puts it pretty close to an acetylene, a little longer than acetylene, CC, whether this bond here is a quadruple bond or something closer to a double bond. a number of papers have been done about this, but I'm interested more, let's see, I think chemistry is about transformation. I think the interaction of theoretical chemists with chemists is most productive when we talk about things you can change. That's transformation. So what interests me, or what my focus comes to mind, and what the picture I'm going to give you gives is the change that makes for the difference, I want you to notice something else. This C2 molecule is a microcosm of all of chemistry. If you think about CC distances in angstroms of CC bonds, single, double, triple, in the 500,000 organic compounds that contain them in the Cambridge structural file, you will get, I didn't show you that, but you will get that the range of those bonds is between 1.20 for acetylenic type compounds to 1.54, as you saw, for ethane. Everything is in there. What I want you to see is the C2 molecule in its ground and excited states is playing out the full range of CC bonding in any molecule. So if I understand this, there's a sign that I can understand the other ones too. So now let's go back to high school and graduate school. This is the bonding for C2 at a high school level. 2s in phase, out of phase, 2p sigma, 2p pi, pi stars, sigma star. I mix in S and P through second order perturbation theory, I would say. Some might say it another way. And you get the lowest sigma G is bonding, the upper sigma G becomes a lone pair combination. Okay, so I can assign a bonding character to these. And what I want to tell you is that qualitative picture is, I would claim, much more powerful than any bond index you use to quantify it. Because in that qualitative picture is where understanding resides. The numbers are what the numbers will be according to the various measures. And if you calculate the bond index with Levdine population analysis, you will get a different number from a Mulliken population analysis. But that this will be large and this will be small, that will not differ. You will just have to push me on what large and small is, but that it is that is where understanding resides. So what are the different states of C2? Well, the ground state has, remember this, usually when we tell students about this, we tell them about N2. N2 has 10 valence electrons. These two, and this is filled. So N2 is filled through the 2 sigma G. And N2 has a triple bond. Where's the triple bond? Here's the sigma component. Here's the pi component. N2 has 2 lone pairs. I'm asking you to draw a Lewis structure in your head for N2. Here is 1 lone pair combination. Here is the other lone pair combination. What is the first orbital that you ionize out of N2? It's the 2 sigma G with a lone pair combination. What are the bonding characteristics? Very bonding, slightly anti-bonding, bonding substantially, and slightly bonding. Here's the ground state of C2. Okay, now switch your thinking from N2 to C2. 2 less electrons. It turns out that this electron is vacated, the 2 sigma G. So the pi u is the ground state, but as you can see from this picture, that pi u is not that far below the sigma G. So that a triplet with 3 electrons in pi u and 1 in sigma G, is actually competing to be the ground state and is only half an EV above, or less, actually, I think. But when I promote an electron from a very bonding orbital to a slightly bonding one, okay? Am I going to lengthen the bond or shorten it? I'm going to lengthen the bond a little bit, losing some bonding. And the bond lengths in that one, they're over, these 2 states over here, are a little longer. If I promote 2 electrons to sigma G, from this one to that one, I will lengthen it more. I can make sense out of every equilibrium bond length qualitatively by this kind of bonding argument. Let me in particular try the hard one. How do I get a bond length that's shorter in the ground state that's shorter in an excited state than it is in the ground state? That's this minimum here. How can I get that? What I need to do is to take an electron out of a slightly anti-bonding orbital and to put it into a slightly bonding one. That's all I have to do. I understand that. I can understand the very long bonds. I can understand the short ones. Not quantitatively, or I have faith my colleagues will get it right for these curves, but qualitatively, I am very happy. I have made sense of a lot of chemistry. And that C2 is not only there in this molecule in a vapor phase. Let me show you some molecules we don't tell our first-year students about. There are molecules like erbium-10, ruthenium-10, C19, or uranium-2, chromium-2, C5. All of them have C2 units in it. Here is a structure of one of them, a simple one. Sometimes we tell students about calcium carbide. Calcium carbide is a rock salt structure of calcium 2 pluses and C2 2 minuses with an acetylenic bond length. But these molecules, here's one of them. It has a layer of dysprosiums and then a layer of cobalt carbide, an organometallic polymer, which has C2 units, which are pi bonded to 1 cobalt and di-sigma bonded to 2 other cobalts in blue. And that C2 unit has a bond length of 1.36 dysprosium cobalt carbide. Sorry, that's not quite here. It is 1.366 from an X-ray structure. And how do I make sense of that? Of course, I'm going to make sense of this by doing a band structure calculation. This is a 3-dimensional material. I know how to do band structures, and I've taught chemists how to do it. I'm going to do a band calculation. I'm going to look at the population of various C2 levels, C2 as a fragment, and I'm going to see which are occupied. It'll give me something approximately. C2, the world of C2, diatomic molecules, organic molecules, organometallic molecules. My colleague Pete Wolzanski has made a C2 trap between two titaniums, I think, here, and siloxy groups. Here's a C2 being attacked by 4 rutheniums. Here's a C2 inside a polyhedron of calciums and nickels. Here is a C2 on a surface of silver 100. This is spectroscopy, that's organic chemistry, that's organometallic, this is solid state, this is surface chemistry. The molecule is trying to tell us something. It's trying to tell us something that you guys can call yourself whatever you want. There is one chemistry under all this. And it's time to see that one chemistry. And a fragment way is not a bad way. So I now come to the end of the story. I wanted to get in my way. I think the simple MO way is still a reasonable way to especially look at how the reasonably persistent connection between atoms, that is a bond, measured in a number of theoretical ways, a number of experimental ways, how it can be varied and be of use to chemists. I've shown you, it took me 2.5 hours, but I was able to go through many of the things that chemists use. The discussion continues, and when you distribute the PDF, you can get some of these more recent discussions of covalent bonding by people I respect and admire, in fact. But I want to come with my end view, which is part of a general worldview of chemistry. I think that any rigorous definition of a chemical bond is, if you think about it, that by itself is just as productive as calling one human being white and another human being black, that you have a bond or no bond. It leaves one with the comfortable feeling, yes, I have a bond, I do not have a bond. But what else does it tell you? And yet, this bond is very important. It's important. It has a history, has a life, it generates controversy. Look at discussions to this day about hydrogen bonding, about sigma holes, about other things. And also, it's interesting that it has these different things. From time to time, there come up people from physics who thinks they can give us the answers, that you stupid chemists just haven't found the right way to define a bond. Well, it's okay. I'm used to that because I move in both worlds, but I can, if they give me the time, I can show them the full beauty and what the problem is in these definitions. My advice is always be aware of the different criteria and accept at the limits that a bond will be a bond by some criteria and maybe not in others. And in fact, I would say, look for those borderlines and especially think about how you can manipulate it. Just respect the idea that this is not that carefully defined and that it has various manifestations. I know it's hard to be aware of all of them, but calculate the bonding in a number of ways if you're a calculator. If you're an experimentalist, express some due skepticism about some of the theoretical methods, and always ask the question, how can I change it? How can I probe my understanding by changing it? Thank you very much.
Thank you, Professor Ward. Thank you very much. It was wonderful. Thank you. Well, I have been waiting for asking you 2 questions from the people in YouTube.
Sure.
Okay. So the first one is from, let me see, Eduardo. Eduardo says, hello, Professor Hoffmann. Do you believe the secret of superconductivity in room temperature could be hiding in some place in chemical bonds?
So, as many of you know, I have been working close to the border of chemistry and physics for the last 25 years and for the last 10, 15 on materials under high pressure, which is where some of the new high temperature superconductors have come from. I have studied superconductivity. I have understood a part of it, and I think that a part of the theory of superconductivity leads one to think, this is from a point of view that the superconducting pairs of a BCS model can be thought of as being correlated over very long distances, nothing like a chemical distance. Part of the theory of superconductivity leads you to think that you will not find a chemical explanation or method. Maybe it's naive, but I believe that you can find one. And I think that you can find a chemical approach, and it will be based on a good physical chemical understanding of electron-phonon coupling, so that a phonon is just another word for molecular vibrations. So that understanding how electronic structure changes with vibrations and visualizing it could lead to a chemical theory of superconductivity. I've felt close to it in my later years of activity, but I didn't get to it. I couldn't see. When I say I didn't get to it, as you know, first of all, if I got to it, you would hear about it, because I love to write papers, and I've written 650 of them. Second, I like to teach. So the moment I understand it, you will understand it, because that's what I am. I'm a teacher. I just haven't gotten to it. I haven't gotten it in a shape that is tangible, that I can teach to you, or that I understand. I think a chemical theory of superconductivity, meaning that you could predict the elements and the stoichiometry of the next superconductor, that is a reasonable one, maybe not the TC, but that it should have a high TC. I think that is within the reach of chemists, and I think it's not that far away from us, but I will not be the one who gets it.
Thank you. There is another one. In the energy decomposition analysis you showed, the Pauling term is repulsive.
Yes.
But if you look at things from the quantum theory atom in molecules perspective, the Pauling terms is attractive. Do you have some thoughts on this?
I think they just have different ways of defining what is the Pauli term. The Pauli term in the fragment analysis is defined as what you get after anti-symmetrizing the wave function properly for the two fragments. That is, and that I think that there's a different definition of what the poly term is in QTAAM and the fragment analysis. I'm just not well enough up on these to be able to explain it.
Mm-hmm. Okay. So just now is a personal question. Sometimes I see that the students want to run the most accurate calculations from scratch. The first thing they try to do is to run the highest level calculation. And sometimes I think that it's better to start with a lower level method, try to understand the chemistry, and then, if necessary, goes to a higher level. Do you agree with this strategy?
Yes. Oh, sure. And also, model or toy systems are immensely useful. You can see the utility of a harmonic oscillator as a model system for molecular vibrations, and then to introduce anharmonicity. But the most fundamental and basic model system for underlying chemistry is the particle in a box. And that toy system, elementary system of quantum mechanics, which can be then modified by perturbations or by having several boxes, but that the ideas of the levels of a particle in a box, that the number of nodes increases as you go up in energy, that idea is there throughout all of chemistry. And you can model a diatomic molecule by a particle in a rectangular box, and you get things pretty well. You can model the orbitals of a polyene, the pi orbitals now, by a particle in a box. Anyway, I think if I examine why did I get so much chemistry out of a bad theory in the first 15 years of my life, before I started doing all electron calculations, or 20, 25 years, I did extended Hückel calculations, which are just molecular orbital calculations with an extended basis set. And I had the base, but what I had was a simple model whose conclusions were sometimes right, sometimes not. But I had the explanations for what levels did in terms of which levels interacted and how they interacted were amenable to a simple perturbation theory analysis, which could be formalized. And I immediately translated it from equations to words. And that's what made it teachable to other organic chemists. Whereas the people who stuck with the equations had more trouble teaching the things. They had the same things, but that the two levels mix, that the lower one has no nodes and the upper one takes the node, that the lower one mixes in the upper one in a bonding way, whereas the upper one mixes the lower one in an anti-bonding way. These were such, there's a perturbation theory basis, but somehow I could play with it. So the other thing that I would advise students, I've already said it in some way, when they are given a simple model, which may mean for organic chemists some software like Spartan or some minimal basis set ab initio calculation or DFT. The first thing you should do is get yourself in a frame of mind where A, you do things that you know. I've already said that a few times.
Mm-hmm.
And second, play with it. Play. You've been given a toy. It doesn't cost much to do another calculation. So use the playing, meaning do another system. If you've done H3, do H4. If you've done a ring, distort the ring. The playing is for a purpose. The purpose is to sharpen your skills for understanding why the calculations as perturbed by you as a result of the game are coming out the way that they are. That playing the game builds it gets you no science necessarily, but it builds your confidence in your ability to understand the calculation, so that the calculation is not a deus ex machina that gives you a number, but is something which reflects what you do to nature in a perturbation.
Okay. There is another question here. Let me see. Oh, it's from my friend Antonio Carlos Pavão.
Hello, Antonio. Hello.
Pavão said, "Dear Roald, great to see you. I heard you said, if you want certainty in your life, go to math. Does it mean abandoning the desire or illusion of finding the theorems of chemistry?"
Yes. Yes. So where that phrase, the theorems of chemistry, comes is in part from that wonderful book by Primo Levi, The Periodic Table. And in one chapter at the end of his education, he's disillusioned with the analytical chemistry he has learned. And he asks, where are the theorems of chemistry? And it's a question that young people who are mathematically minded often ask. Also, the ability for science at the initial levels is often revealed by the ability to do mathematics. I'm thinking now of elementary school levels. And so there comes a what I would claim not a false alley, but a little bit something that misguides you, that the numeric is the absolute and the algebraic and geometrical are certain manifestations of it. But I think that theorems, it's such a satisfaction when you can prove a theorem in the classical way of Euclid. And chemistry is not like that. And what I always want people to say is, look, you have proven in your relationship with your parents and siblings and teachers that people are not theorems. And furthermore, that knowing what people are like, who they are, is a process of admitting more and more complexity. That complexity is interesting. It's inherently human. It's not reductionist. So I would say really that molecules are like human beings, or I would like to move in that direction rather than the direction of theorems. And yet we have ways of understanding this world. It's natural we try to understand it. But yes, I've given up on complete understanding.
Okay. So I would like to be with you for the rest of the day, but I think it's time for the last.
It's time. It's time. Thank you for giving me this opportunity.
Just one, the last question. This is just a curiosity. It's Michael who is asking. What has inspired you to become a poet? And how hard or easy was it compared to chemistry?
So what inspired me was a course at the university in poetry. And a teacher, Mark Van Doren, a poet himself, who taught me how to read a poem and taught me the power of words and resonances and alternative meanings. And that just seemed to me so wonderful. It also seemed that it was within reach, that I could do it. I worry about music and mathematics because those seem to require talent. But chemistry didn't require any talent. And poetry, anyone can write, and people do, or at least I could. With time, I became good at words, and that served me. It is more difficult. I'm a good chemist. I'm an average poet. It does not come easily, but when it comes, and I have persisted in it, and I have, of course, tried to publish, maybe carrying over what I did from the science, but also I want to share it with people. It's been wonderful to see the power and the ambiguity of words.
Okay.
Thank you.
Thank you. And there are other people here. Thank you. Thank you, because you have inspired them when they were selecting the field to study. So some of our friends here say that they decided to go to chemistry because of your work.
Thank you. Thank you
very
all.
much.
And you will distribute the PDF if anybody wants it.
Okay, I will do that. Thank you very much.
Thank you. Bye-bye.
It was a honor. Thank you.
Bye.
Bye, Professor.